Hello students, I welcome you to this session, the video lecture on the third chapter of module 2, that is discrete logarithm and its application. So in this chapter, we are going to learn the basics of discrete logarithm. It would be great if we could recall some modular arithmetic properties that we did in module 1. And then the core essence of this chapter would be the Diffie-Hellman key exchange algorithm that is actually used to securely exchange the shared secret keys between two communicating parties. So before we begin, or before you advance in this presentation, I would want you to, take a look back at module 1 and recall these concepts, that is the properties of modular arithmetic, inverse modular arithmetic, what are groups, how do we indicate or define groups, the notations of groups, what is the generator of a group, what are cyclic groups, and so on. So please be prepared with these concepts. Try to recall, go back to the concepts you've studied in module 1 and have an idea of the basic definitions of how these concepts work. So let's consider the basic definition of a group. We have already known that in module 1 that group is a basic algebraic structure which is denoted as a pair. If you can recall, the pair had the notation G comma star, where the first element of the pair, that is G, was a set and star was a binary operation. So if I consider this multiplicative group that is given here, if I say this is the group given here, ZP star, right, star P, then I can say that ZP is actually the set and star is the binary operation. Star is nothing but multiplication. That's why this group is called as multiplicative group. So let's assume that P is always a prime number. So that's about the definition of group. And you should also be able to recall that the four properties a pair should hold in order to be a group: the property of closure, associativity, and every group should have an identity element. You can obviously see that the identity element of a multiplicative group is 1, and every element in the group or in the set ZP star should have an inverse element. And we have seen how we can compute an inverse element, right? So next we move on to recalling the concept of generator. So any element in the set ZP star, if that element can generate all elements of the set ZP star, then such an element is called as the generator of the group. So how do we generate the elements of the set? We have this formula, right? We applied this formula, or this modular exponentiation, that is G, take the generator element, raise it to the power 1 mod P. It should generate an element. G raised to the power 2 mod P. In this way, we continue till G raised to the power of P minus 1 mod P. And whatever values this modular exponentiation operation or function generates, all of them should belong to this set ZP star. Not just that, G should be able to generate all the elements of ZP star. Only then we say G is the generator of the group. Now let X be an element from the set 0 to P minus 2. Suppose P is a prime number which is 13. Then X can be any element ranging from 0 to 11. Then we can define the modular exponentiation function. The modular exponentiation function you can see as defined here. Okay, we have defined it here, this one. Y is equal to G raised to the power of X mod P. So in this function or in this equation, we call G as the generator, or G is the base. We call P to be the modulus, the modulo operator. Okay. And if we inverse this function, if we inverse or compute the inverse of this, we get this function or this equation, and that is called as discrete logarithm. So discrete logarithm is defined this way: X is equal to log Y to the base G mod P. Again, understand, G is the generator or the base, P is the modulus. So this is, these two formulae will be used in the next slide to compute some simple problems on discrete logarithm. So I would want you to stop here. make a note of all these concepts. So I hope you have recalled what is a group, what is a generator, and how a generator generates all the elements in the group or in the set ZP star. Take down the formula for both modular exponentiation and discrete logarithm, and then proceed to the next slide. Okay. So let's look at this problem. Find the discrete logarithm of 28 to the base 2 modulo 53. So from this problem statement, we can pick some of the defined variables. They have said base 2. So we know what is the notation of a base or of a generator, G. So we have defined G to be 2, right? G is 2. They have said modulo 53, so you know the value of 53 is the value of p is nothing but 53, and they've asked you to find the discrete logarithm, so you have to find x given the value of the next unknown, the only unknown, that is y. So y is 28, g is 2, p is 53. All this I have gotten from the problem statement. Now I have to find out the value of x. So let me use the first formula, that is the formula of modular exponentiation, and let me substitute all the known values which are defined in the problem statement. All I have to do is find the value of x. So how do I find the value of x? So I have to write this. This is the unknown I have to find. So how do I find it? 2 raised to the power of something modulo 53 should give me the remainder 28. That is what I have to find out. So let me start with 2 raised to the power of 1. 2 raised to the power of 1 is 2. 2 mod 53 is nothing but 2. 2 is definitely not equal to 2 raised to the power of 1. If I write 2 raised to the power of 1, is nothing but 2. 2 mod 53, what is the answer I'll get? I'll get the answer as 2. It's definitely not equal to 28. So if you continue in this way, 2 raised to the power of 3. I'm sorry, 2 raised to the power of 2. Let me write 2 raised to the power of 2. What is this? This is nothing but 4, right? 4 is 4 mod 53. What is 4 mod 53? It's nothing but 4 itself. Definitely not equal to 28. So I am going to continue in this way, and this way I will continue till I get the value equal to 28. So when I completed the substitutions and continued further, I advanced the value of x or incremented the value of x, and when I reached x value as 16, when I did 2 power 16 and then the modulo 53 operation, I definitely got the remainder 28. So in this way I found the value of x. You can use your calculators and keep performing these operations in a loop. So this is how you can find a discrete logarithm value x of given the values of the base of the generator, the modulo the modulo value, that's the value of p, and the value of pi. So in the similar fashion, I want you to solve the next problem, that is find the discrete logarithm of 72 to the base 2 modulo 131. So before you proceed further, I want you to stop here, apply the same modulo exponentiation formula, substitute the values, and continue to the next slide. Okay. So now we, come to the core essence of this chapter, that is the Diffie-Hellman key exchange algorithm. So let's look at how this algorithm or how this DHA protocol works like. Okay. So I am going to have two communicating parties here. The first one is Alice. So I'll call this party as Alice. Okay. And I have the second party. I'll call this party as Bob. Okay. So Alice and Bob want to communicate with each other, and they are going to use the Diffie-Hellman key exchange algorithm. And as step one of the protocol, they are going to decide or agree upon one common, parameters, or two common parameters. That is a prime number p, which is a large prime number, and a generator G. We already know what is a generator or what is a base, right? What is a generator of a group, of a set? We already know that. So they are going to agree upon this. So P and G, you can see the values P and G are agreed upon, negotiated between the parties Alice and Bob, and they are shared on this network. Using this network, P and G values are shared between Alice and Bob. So if I have an attacker here, let me call the attacker C, he can sniff on this network and definitely get the values of P and G. So what I'm trying to tell you is that P and G are available in the public domain, or anyone can know the value of P and G if they sniff onto this communication medium. So that is all right. Let's go on to the second step. The second step says they generate their own private key. So how does Alice do that? Let's see how Alice does that. So here you can see Alice picks a random number, a random integer A to be her private key. So the condition is this: pick an integer randomly, but the range of that integer has to be in between 1 and p minus 1. What is p minus 1? We already know p is a large prime number agreed by Alice and Bob. So I do p minus 1 and I generate a random integer between 1 and p minus 1, excluding 1 and p minus 1, and that is Alice's public private key. Bob does the same thing. That is, he also picks a random number b, and again the condition for the random number is the same. That is, the random number should be between p1 and p minus 1, and let's call that Bob's private key. So you can see the private keys are no way exchanged on this public domain or on the network. A's private key is known and safe with A. B's private key or Bob's private key, small letter b, is known only to Bob and not even known to Alice because it's not shared at all. They keep it secret within themselves. Let's go to step 3. In step 3, okay, they are going to calculate their own public keys. That is, let's see how Alice and Bob do that. Um, let me start here. So you can see Alice uses this formula to compute her own public key. So G raised to the power of A mod P. What is G? G is nothing but the generator and or the base that is shared on step 1. So we know the value of G. What is A? Small letter A is Alice's private key known to Alice, so she can still use it in computation. And what is P? P is the very large prime number we selected in step 1. So when Alice performs this computation, what she gets is capital letter A. Let's call this capital letter A as the public key of Alice. What does Bob do? Bob goes back, does the same computation. That is, he uses the same generator G, this time raises it to his own private key. What is Bob's own private key? Bob's private key is nothing but B. So you can see Bob has raised G to B, performed the modular arithmetic using P, which is a large prime number which both Alice and Bob knows. And what do they do after that? Once Bob computes his public key, he sends it over to Alice using this network. And once Alice computes her public key, she's going to send it to Bob over the network. So is this available to C? Yes, definitely. So now C has access to this prime number P. C has access to G, the generator. C also has access to the public keys they have exchanged because he's been intercepting the communication happening on this network. But he does not have access to the secret key A, I mean the private key A and the private key B. Now Alice has received Bob's private key, Bob's public key. Bob has received Alice's public key. So what do they do? So you can see that what Alice has received is here. Excuse me, Alice has received is here, right? B. What is B? G raised to the power mod B. What does Alice do now? To compute her own shared secret K, Alice is going to take what Bob has sent as public key, raise it to the power of her secret key, apply modulo arithmetic. What is Bob going to do? Do the same thing. He has obtained Alice's public key capital A. He is going to raise it to his secret key mod P. Let's substitute what is B. What is B? GB mod P. Not that, see, now Bob will know the entire value. He will not know the constituents of this. Only one value. GB mod P. Raise it to A mod P. Perform the properties. Use the properties of modular arithmetic, and what Alice computes is g raised to the power of ba, which can also be written as ab mod b. And what Bob computes is g raised to the power of ab mod p. Ta-da! It's the same. So this is the shared secret key. So let's revise this again. You can see that the intruder or the attacker sniffs over the network. He will still have access to the prime number, the generator, the public keys generated by both Alice and Bob. He will in no way have access to the secret of Alice small a, Bob's secret small b, or the shared secret k, which both Alice and Bob know. Now let's look at Alice's domain. Alice knows PG, Alice knows her own public key. Alice knows B's public key. Alice has computed the shared secret. And Alice has a private key A known only to Alice, not even to Bob. Let's go to Bob's domain. He has PG. He has his own public key. He has Alice's public key. He has his own private key, not known to anyone, small letter b. And he has computed the secret. And using the Diffie-Hellman key exchange protocol, you can see that both Alice and Bob arrive at the same shared secret using modulo arithmetic, discrete logarithm, using the public key, using the private key, using groups, because you have the prime numbers and you have generators. So all these concepts have been, incorporated in the Diffie-Hellman so that they arrive at a shared secret without having to actually share the secret with each other. You can see this K, okay, is no way arriving on the network. They have computed it by themselves. There's no way they're sharing it on the network so that the intruder can see it or spoof it. So in this way, this is how they Diffie-Hellman protocol proposes to securely exchange shared secret keys on the network. Let's move on. This diagram illustrates the same thing, so I won't be spending much time here. You can see A and B computing their own private keys, computing their public keys. I'm sorry, selecting their private keys randomly, computing their public keys, exchanging it with each other, computing the shared secret, ending up having the same calculated shared secret. Now, one problem in the Diffie-Hellman protocol, you can see that an intruder can spy over the communication network and he can have access to P, that is the prime number. He has access to G, the generator or the base. He has access to the public keys of both Alice and Bob. This much is the information he has obtained by sniffing the network. Given this information, can the intruder compute GAB mod P or compute the secret? That is the question. Can I compute? To compute GAB, all I need to compute is the value of small letter A, right? And the value of small letter B, because I know the value of G and I know the value of P. All I need to compute is this. So let's go back here, right? So you can see Alice and Bob both have computed their public keys using modular exponentiation. So G raised to the power of A mod B. Suppose G raised to the power of A mod B, say, gave me a value 131. Okay, suppose once I finish this, I'm Alice, and once I finish this computation, I got 131 as my public key, which I'll be sending to Bob. Once I have this value, computed value, there is no way anyone can find its constituent parts. That is, given the total value, I cannot find what is G, what is A, what is P. Similarly, if Bob computed his public key and say suppose the value was 61, given the value of 61, there is no way I can backtrack and find out what was G, what was B, what is P. So given a total value, there is no way I can go back and compute its constituent values. So this property of discrete logarithm or modular exponentiation is called as one-wayness. That is, you can go only in the forward direction. You have the value of GAP, you can compute the formula G raised to the power of A mod B. You can compute this. But once you have this entire formula, the value computed, there is no way you can work back and get its constituent parts. This is called as one-wayness. because of which, even though an intruder has these values, he cannot generate the value of A, he cannot generate the value of B, and hence he cannot generate this shared secret, even though he's sniffing the communication network. This is called as the one-way property of discrete logarithm, and this itself ensures the security of the Diffie-Hellman protocol. Okay. Another way to overcome this problem would be to choose a very large value of p, which makes it computationally intensive and hence infeasible to go backwards. Even if someone found a way to go backwards, which is not possible, but which is not, I would not say impossible, I would call it infeasible. So by generating a very large prime number, it makes it computationally intensive and even more infeasible to go back in the reverse direction. So that is your Diffie-Hellman computational problem and the solution to the problem. Okay. So let's see an example. So you have Alice and Bob. They have their public numbers. They have the prime numbers and the generators, which are known even to the intruder. And then Alice randomly selects a private key. Bob selects randomly another private key. You know what is the condition for random generation of integers? Both the integers should be in between, or in the range of 1 to p minus 1, excluding both 1 and p minus 1. Alice and Bob go ahead, compute their own partial public keys using g raised to the power of private key mod p. They exchange their public keys. Once they exchange their public keys, so you can see here, once you exchange the public key, what happens? 1 second. So you can see here, Alice receives Bob's public key. Is y is equal to 16 Bob's public key? Yes. And Bob receives Alice's public key, which is nothing but 6. Yes. So what does Alice do now? Raises that public key to the power of her secret key. What's her secret key? A is equal to 4. Raises the public key, which is y, to the power of 4 mod p. Computes the shared secret. Bob takes Alice's key, what he has received, raises it to the power of his private key. So have we done that? Yes. X raised to the power of p, again computed the shared secret. So 9 is the shared secret. So this is what they have done without actually exchanging their, what do you say, their private keys or the shared secret. Let's move on. So if we look at this scenario, the same Diffie-Hellman exchange protocol is being used here. Alice and Bob are trying to communicate with each other. You can see Alice has chosen a random number A. Alice has computed her public key and is sharing this information. G and P are known to both. So she's sharing G and P as well as her computed public key to Bob, thinking Bob will receive this data or this information. But there is an attacker in between. Let's call this guy C. So there is an attacker C in between who is intercepting this communication. So what does the attacker do is he blocks this data from receiving from Bob. Okay, and instead he knows the value of P, so he knows he has to generate a random number C between 1 and P minus 1 because P is sent in the clear by Alice. He computes his own public key G raised to the power C mod P because he knows that's how it is done. And instead of sending Alice's public key, he sends his own public key along with G and P, which are sent in the clear and known to all to Bob. Right? So now Bob has no way of understanding if this information has he received it from A or from the attacker, because no way Alice has said, "Hey Bob, I'm Alice and I'm sending you this." No, Alice has not authenticated herself. She's only sending or requesting to talk to Bob by calculating a public key and sending it over. But Bob has no way to know. He is only thinking that he's talking to Alice. But even if somebody else tries to, clone the identity of Alice, there's no way Bob knows it because Alice does not authenticate herself here, right? So B is still thinking he's talking to Alice. So B chooses a random number, B, and he computes his own key, sends it to or sends it over the network. See what the attacker has done again. He has blocked B's public key from reaching Alice. He has read the public key, and what he has already computed here, he is sending the same thing to Alice. right? So now the next step, computing the shared secret. What has Alice received? She has received GC mod P. So she can raise this to the power of her secret key and compute GAC mod P. She's thinking C is, this is Bob's public key, but no, this is the attacker's public key. Let's come to Bob's side. What has Bob received? Bob also has received GC mod P. He will raise it to the power B because B is his secret and compute this. You can see Bob has a different secret from Alice, who shares a common secret with both of these, the attacker C. Why? Has attacker C computed G raised to the power of AC mod P? See here, he has got GA mod P. Can he raise this to the power of C and get GAC mod P? Definitely. So see here on this side of B, he has received GB mod P. Can he raise this to the power C and get GBC mod P? Definitely. So you can see Alice is thinking she's communicating with Bob. Bob is thinking he's communicating with Alice, but actually, both Alice and Bob are communicating and sharing a shared secret with the attacker C. Now, this problem is called as the man in the middle attack. This attack is called as the man in the middle attack because there's a person in between or an entity in between who's trying to intercept the communication between Alice and Bob and behaving like he is Alice or he's Bob to the other communicating party. So this problem can be solved using the RSA digital signatures. If you can recall, digital signatures are a means, just like your regular signatures, of authenticating the sender. If I send a document and I sign on it, then the receiver of the document knows that it is definitely me, unless my signature is not forged by somebody else. He knows that this is definitely the person who has signed is sending the document over. So now, if I can, okay, if I can go back to this, even if an intruder has obtained this, when he forwards it to Bob, he cannot write Alice's signature. Anything that originates from C will have C signature on this, on the document. So even if C tries to send this to Bob, if it is a digitally signed document, then this one will have C signature on it. Bob will receive this, sees the signature. Uh-oh, this is not Alice, this is somebody else because I have it digitally signed, and definitely this is not Alice's signature because Bob already knows Alice's signature. How Alice's signature knows. Maybe in a prior interaction, Alice has exchanged or shared her signature with Bob. So he knows there is an authentication database which has Alice's signature. So when he does the matching, no, this is not Alice, this is somebody else. So Bob definitely knows this is not Alice, this is an attacker because he sees that this is not Alice's signature and immediately terminates the communication. So this is one way of using RSA's digital signatures in conjunction with the Diffie-Hellman key exchange algorithm to avoid the man in the middle attack. So yeah, so before we close this chapter, I would want you to compute the shared secrets using the values of P, G, and the shared secret of Alice. I'm sorry, not the shared secret. Private key of Alice is 8, and the private key of Bob is 10. And in the second problem, the private key of Alice is 10, and the private key of Bob is 13. So before you close, please review the DHA protocol. Use the same protocol. The steps are very clearly mentioned in that algorithm. Use the same thing and try and compute the shared secret that Alice and Bob would have computed if they had this given values. So thank you for watching this video lecture. If you have any concepts that require clarifications, I'm going to initiate a discussion thread on the Canvas classroom, and we can discuss there and we can solve the problems using peer-to-peer interaction if I'm not available, or I can get back and solve these problems on the forum. Thank you.